Welcome to this presentation on the application of artificial intelligence in the field of corrosion. I'm Nick Birbilis from Deakin University, and it's a real pleasure to have this opportunity today. So a special thanks to the conference organisers, and indeed I will give thanks through the presentation. However, I'd like to acknowledge the traditional owners of the land from which I'm coming to you today, and that's the land of the Wurundjeri people, and I pay my respect to their elders past and present. Some of the work I present today has been supported by ONR, Duratec, and BlueScope Steel, and I acknowledge them along with my previous institution, the Australian National University. All right, so artificial intelligence, or AI, is generally defined as the intelligence demonstrated by machines as opposed to the natural intelligence displayed by humans. The term AI was first coined in the 1950s by Alan Turing and popularized during the now famous 1956 Dartmouth College Summer Conference. Now, with recent advances in computing and computing cost, AI is already becoming commercially ubiquitous in our daily lives. So from web engines to self-driving cars. So AI, specifically a class of activity called machine learning, relies on learning. So I wanted to introduce a learning example for those that are not familiar with the topic. Let's say I show you this image and I tell you that this is Coca-Cola. So now you've learnt this. So you know the answer to what is this sign. So all good. So by the way, I should say my work has no affiliation with Coca-Cola other than I drink a lot of it. So now if I show you this, what do you think the answer would be? And how about if I showed you this? Or this? Or how about these? Would you know that the answer is Coca-Cola? Now, if you say yes, which is probably what you're going to say, what may interest you is that none of these images in this montage actually have Coca-Cola clearly visible. Some have the word Coke and others are different products altogether. So what you have seen is human learning, but through algorithms, computers can learn like humans. However, what is critical is that there needs to be training data, and the training data needs to be labeled. So objective machine learning cannot self-train without objectives. So at least not yet. So today I will show a few examples of different classes of activity that sit under the banner of artificial intelligence. All of them are unique methods, namely computer vision, machine learning, natural language processing, and generative adversarial networks. An example from each in the context of corrosion is provided. So in the work of students Will Nash and Ben Burton, corrosion detection is automated using computer vision. Today, deep learning techniques are most commonly used for computer vision, and convolutional neural networks, which provide a multi-layered architecture, allow neural networks to focus on the most relevant features in the image. So the model architecture for a corrosion detector model is shown here. You have an input image, and through a series of layers, the outcome is either corrosion or not corrosion. The process that goes on in convolutional neural networks is that there's an operation made on the input, where the input is an image. Image is really just a matrix of inputs data. And this is shown sort of in this GIF image here, where you can see the kernel mask transforms the input data towards an output target. So in the training process, the input data is labeled as having corrosion or not. So the model learns what decision process is involved in labeling if an image has or has not got corrosion in it. And deep learning can also be represented by this example, and that's a process that links inputs to outputs. So you have an input, you have feature extraction, classification, and an output, a car or not a car. So Will Nash developed the web tool found at corrosiondetector.com. This tool allows users to input an image, and a deep learning model based on training from an expertly labeled dataset will tell you if the image has corrosion or not. Now, the model also lets users interact with the training process by participating in labeling images as to whether or not they have corrosion, and also allowing users to upload their own images that may or may not have corrosion. So in this work, the model, over a period of 5 weeks of user interaction, so these are some examples here, saw over 300 images uploaded and many thousands of images labeled. The model improved its accuracy via tuning of the algorithm's hyperparameters from under 70% to about 95% accurate in terms of being a classification tool, whether or not an image has corrosion in it or not, which is actually quite remarkable. So here's an example from Corrosion Detector. Feel free to check it out. And you upload this image and it says there is corrosion in your image, which is fabulous. But more recently, and I'm excited to share some of these results, and when I mean recently, as in this year, a student, Ben Burton, enhanced the functionality of Corrosion Detector and created RustSeg. And you folks can find this at rustseg.com. This deep learning model actually seeks to not only determine if corrosion is or isn't present in images, but uses advanced algorithms to isolate pixels in the image, pixels in the input images that are responsible for triggering the decision as to whether corrosion is present or not. This is done by an architecture that takes images determined to have corrosion by a classifier and then uses a GradCam tool to create segmentation. So with further training, whereby Ben used many thousands of images, a lot of them coming from Flickr, and also images that did not include corrosion in them, but may be confused for corrosion. So things such as bricks, sand, dirt, cocoa puffs. The GradCam architecture was able to really handle this very, very well. And in case you wanted some maths, the architecture behind this is a sum of partial derivatives. And this performs the segmentation automatically to a high degree of accuracy. And that can be seen here, where you see RustSeg has detected corrosion in this image, and it gives you the prediction score. But what you can also see is that classification type of process here, or segmentation process rather, where you finally get a result that actually has a mask on the pixels that are the ones that give the decision for whether or not corrosion is there or not. Now, one can readily imagine, I hope, how practically useful this is, particularly in industrial cases, if you're looking at, say, industrial equipment. Interestingly, I'm often asked how long this segmentation takes, and what you can see here is that for Ben's RustSeg work, depending on your configuration of computer, a normal CPU may take about a second to classify if corrosion exists or not, or up to about 3 seconds with a less fancy CPU. However, a CPU with a GPU brings down the classification to a very small fraction of a second and does the segmentation process in a small number of seconds. So one could imagine that this could be improved in the future. However, this is already significantly faster than a human. So interestingly, the new AMD Ryzen processors that are common in new Tesla vehicles are even better than what is shown here. So superhuman classification is here with us already. Look, in this next example, we're going to explore the work of Shujing Zhao that was using natural language processing in the search for chromate replacement. So this is a different type of AI. So a couple of years ago now, a paper by Shitsoyan and co-workers was really interesting because it used unsupervised word embeddings in papers to extract information from written text without a human involved. This is interesting because most information amassed by humans to date is actually in the written form. Now, I'm going to spend a bit of time trying to explain natural language processing here. And I do like the example from GitHub that's referenced here. So let's assume for a moment that my name is Jay and that we want to classify my personality. We can give me a score between 0 and 100, depending on how much of an extrovert I am. So let's say I'm a 38, so more of an introvert. So then what we can do is we can actually convert that from a scale between -1 and 1, which is pretty easy. So that would make me something like about a -0.4 in the extroversion scale. Now, let's add another dimension or another trait so that you can know me a bit better. Let's say I'm 0.8 in the next trait, and that next trait could be anything. It could be my love for corrosion or something like that. What we can now do, as you can see on the screen, is we can draw a vector that represents my traits, with that vector representing my personality based on 2 traits. And this can now compare me to other people. So if I was to get hit by a bus and you need to replace me, you can see based on these vectors, from person 1 and person 2, that person 1 is a little bit more similar to me. But what about if you wanted to replace me based on 5 traits? So it's now impossible to draw the similarity because it's too complex. The visual cortex can't do it. And so we've lost the ability to use that visual cortex. But there's mathematical processes like the cosine similarity that can be calculated even for 4 or 5 or more traits. And we can see that that person 1, as you can see on the screen here, is a closer representation of me in case I'm really hit by a bus. So when you apply this process mathematically to words and then similarities in words, or even in the assessment of whole passages of written text, we use word embeddings. And at the risk of scaring you, here is the word embedding for the word king. In the work I mentioned earlier, they used a words to vectors process called word to vec, and I'll get to that again in a moment. But again, this type of AI and this type of, I guess, machine learning is about training. So as trained humans, if I was to give you this passage, thou shalt, you probably know that the blank word coming next is not. This can be predicted by computers as well that have been trained using a trained language model with the specific task of predicting the next word. Now, how would they know that? They would have obviously, the computer would have been fed many, many passages of text and realized that after thou shalt, not is a pretty common word. So the current state of the art that Xu Jing is using is a thing called the BERT model. And this particular BERT model began development in 2019 by Google. And by late 2020, so very recently, it was used in almost every Google query. So again, there is pre-training, as you can see in the left there. And we can see here the architecture that Xu Jing has used with the pre-training and the fine-tuning. In the pre-training, so the learning process for natural language processing, the BERT model has been trained on 800 million books and 2,500 million Wikipedia entries. And when you add to that a fine-tuning step, which is trained on task-specific items. Now, what did Xu Jing use as her task-specific item? She used the Scopus API to go over 80 million records, so 80 million papers, and focused on the 6,000 papers or so that focused on corrosion protection. She used the model to actually assess these 6 questions, which are relevant to our time. One of these questions is, hexavalent chromium can be replaced by blank. Great to know what that could be. Another one, as you can see here, out of these 6 questions could be that the best corrosion inhibitor is blank. Tell us what the best corrosion inhibitor is. So when comparing the answers from Xu Jing's work using the BERT model and no human intervention, we compared the results of the BERT model with 3 benchmark papers and reviews that have experts working in the field for many years, making predictions about what might be chromate replacements. It was interesting to find that the word-to-vec model, as previously explored by Chitsuyan, provided accurate chromate alternative results, whilst the BERT model predicted the most extensive related results. But however, what is absolutely certain from the work of Xu Jing is that these natural language processing models, again, based on learning via algorithms and with no domain experience, could essentially capture all the expert human determined chromate replacements that have existed since the beginning of time. So the prospects are obviously significant, and the speed at which someone can start to run with this technology is quite remarkable. So look, in this third example, we're using machine learning for alloy design, and I'm going to describe some of the work from Joseph Mangos and Marzi Gourbani here. One can imagine in alloy design, if you have to change one variable, so if you look at this plot, for example, you could think of the effect of, say, copper in aluminium. Increasing the extent of copper might actually have an impact on strength. If you have additional elements, such as copper and magnesium in aluminium, we use different ways of representing copper links representations where the visual cortex can still be stimulated. But what happens if you have 4 elements or 5 elements or 7, or like our aerospace alloys, you have 10 elements? Well, then you actually need to capture relationships using more complex ways, such as neural nets, a bit like the schematic that's been shown here. For the case of aluminium alloys, you could imagine a series of compositional inputs and additionally some type of heat treatment, all contributing through a very complex set of interactions to lead to a resultant yield strength, tensile strength, and ductility. So to actually capture this as a tool, you already know what we would need. We would need, of course, training data, as you do in all such cases. So luckily, through the hard work of a number of researchers and through a process of extensive data mining, and this is what it looks like. It's literally people, food, and music. We created a database of 1,043 unique alloys with their properties known. And the process of then encoding heat treatments, which is an important step, was also done. So to give a numeric value to the heat treatments. And you can see here the spread of the 1,043 unique alloys that we were testing. So as seen here, the workflow includes training being done, and this uses the major portion of a data set. And weights are applied in the algorithms that make up the layers to create a link between the training and validation data, which then allows the algorithms to successfully forward predict properties from input compositions and heat treatments. So this is in fact what is done and what can be done. And there is a user tool available if you'd like to check it out. You can perhaps use this QR code to get there. And this allows you to predict the properties of any aluminium alloy with excellent accuracy. However, going one step further in artificial intelligence, one may actually employ optimization techniques, right? And this would allow a user to propose a set of target properties that they would want, and then the model would determine a composition and heat treatment to achieve such properties, which is quite remarkable. And of course, this is, in fact, you can probably guess what was done. And you see that by using that tool here, if we wanted a tensile strength of 450 megapascals and a ductility of 10%, we're provided a composition and a heat treatment to do this. Now, I'm not going to dwell on this too long, but this composition, as you can see, is very unusual and is the sort of composition that would perhaps not be picked by a human, but was picked by an artificial intelligence type of model to predict some properties. And for those that know me, you know we love to make an alloy, a good alloy, or even a bad alloy every now and then. And so one can, in fact, then make the alloy, and seen here are some great students, a whole team of them, that weighed the compositional components, melted, cast, rolled, and heat treated the samples to really give a new meaning to what alloy design is and AI-designed materials. Now, our group is currently doing this for a range of alloy systems, and one is again inspired by the potential to be able to use such artificial intelligence to create valuable and useful alloys from confined inputs that, say, for example, might mimic the waste stream. So look out, this is underway in a number of different alloy systems right now, and we're really, really excited by doing that. Now, I promised that the examples would be for corrosion. And if you're paying close attention, you'd realize that I need to qualify why that last particular example I showed you actually was for corrosion, because I was talking about strength and ductility and so forth. But this was actually a model that was developed to create new alloys that are resistant to sensitization. So the tool allows users to also optimize for the degree of sensitization. So the final example, and I fear I'm going to run out of time, and if I do, I'll skip a little bit, is the use of generative adversarial networks for design and discovery of multi-principal element alloys. The area of multi-principal element alloys, which is a sort of a catch-all name that includes the now widely known high-entropy alloy families, is an area that has really exploded in the last couple of years. And a big chunk of why that is relevant to us is that notionally, and I'm not going to spend long on passivity today, these alloys are notionally quite corrosion resistant. And the why and the aspects of passivity we'll leave for another time. But it's natural to want to now design alloys in an optimized manner, and even more rational to see computation on the basis that traditional alloy development has been an expensive and hill climbing exercise over many decades. So generative adversarial networks, or GANs, are a class of machine learning developed by Goodfellow in 2014, so quite recently. And in this case, two neural networks compete with one another, and given a training set, the method can generate new data with the same statistics as the training set. So you create new data, synthetic data, with the same statistics as the training set. So for example, a GAN trained on photos can create new photos, and two examples are seen here. Neither of what you can see is actually real people. They are completely synthetic by different GANs. So GAN deepfakes and one there by style GAN. In the case of multi-principal element alloys, the reason why this approach is really interesting and different to the approach that we spoke of earlier with conventional machine learning based on a lot of data is that there's a complete lack or a paucity of data for multi-principal element alloys. So the use of GANs is one way of creating large synthetic data sets that can then be used for machine learning. So this is the work of student Jipeng Li that reveals a workflow with data generator on the bottom left, making synthetically generated alloy compositions that are then combined into a workflow with training data and processed via a discriminator in order to predict alloys with specific phases. In short, we can consider a case where the empirical design rules for establishing single-phase multi-principal element alloys is what we want to use, and we then have a number of inputs that lead to specific phases as outputs, and high-quality synthetic data can actually help this churn in terms of creating a model that will predict alloys that come out to be single phase. And that's really the whole name of the game for what we were trying to do. But even more so, and this work can be found in the literature now, an approach that we called cardigan. Not only was it done, but it was explored in the case of designing face-centered cubic single-phase alloys that are cheap. So the outputs from this work, can be summarized. And what you can see here is 188 candidate alloys with a density lower than steel, and relative to price is how we've plotted them here, but you could plot them relative to anything. And these were all designed by the GAN model. So in the interest of time, I'm not going to elaborate further. However, again, extremely exciting. And of course, now you know a little bit about GANs as well. So look, in summary, AI is extremely critical in the field of corrosion and protection, perhaps not from obvious examples, because my hope is the stuff that you saw today is maybe something that you hadn't thought of earlier. But all of the examples herein embody part of the future of corrosion engineering in some form. There are ongoing major developments occurring in AI as we speak, and it's a big part of our life right now. So I'm delighted to have shared with you 4 specific and unique examples today, each showcasing at least one AI method, albeit somewhat superficially, but I hope, like me, you've been left very enthusiastic about the prospects and the future. So I know I skimmed over a lot of things, but thank you. And please do not hesitate to reach out with absolutely any questions or any comments whatsoever.